Find the extreme values of f on the region described by the inequality. F of xy equals 2x squared plus 3y squared minus 4x minus 5. On the constraint, x squared plus y squared is less than or equal to 16. So now this problem is going to be a lot of work because this one says less than or equal to. So this means we're not only on the constraint where, hey, this is equal, but that would be just the boundary. But we're also less than, so we're also on the interior of this region. So the interior of the region, including the boundary. So I'm just going to set this up in two pieces. I'm just going to write interior. And that's what we're going to deal with first. And all that is it's taking the gradients, the gradient of f, and find out where it's equal to 0. So I'm finding critical points. And then from there, we take those critical points and classify them. And those can be extreme values, and we'll deal with them from there. So gradient of f is what we need first. So fx. 4x minus 4. And then fy is going to equal 6y, and that's it. So now we want where these equal 0 at. So we're looking for 4x minus 4 equals 0. And if I solve this for x, I move the 4 over, divide by 4. My x is going to equal 1. So I do the same thing for the bottom one here. So my 6y, well, let me write it in order a little bit. 6y equals 0. Okay, because we want my fy equal to 0. Divide by 6, so y equals 0. So we get the ordered pair 1, 0. And that's the only critical point that we have here is 1, 0. Nice. It's nice to when you only have 1 that way. Last problem, we had 6, and it took us a while to go through all of them. Okay, now we have to classify that point. Is it a local min, local max? We have no idea. Is it a saddle point? So what we're going to do is we're going to go all the way back to the second derivative test. What does that mean? That means we're going to have to remember what d was, which is fxx, fyy minus fxy squared. And then from there, we have to determine if these are going to be positive, or if they're going to be, minimums, maximums, saddles, or we're going to know nothing about them. That's the idea. Good thing we only have 1 point. So we're going to need the second derivatives now. So fxx, so I take the x here, I take the derivative of that one, that's just going to be 4. fyy, so I take y here, fy, and take the derivative of that with respect to y, that's going to be 6. And then fxy, that's this here, the 4x minus 4, and I take the derivative of that with respect to y, and that will be 0. So now for the dxy, that's going to equal 4 times 6 minus 0 squared, which equals 24, which is greater than 0. So that tells me I need fxx now. So if I look at fxx and I plug in the 0.10, and I know the fxx is a constant function 4, so I know when I plug that in, it's going to equal 4, which is greater than 0. So that means concave up, which implies 1, 0 is a minimum. Now, since it's a minimum, it might not be the smallest minimum. So now we're going to talk about the boundary of this thing now. So we just dealt with the interior, and it worked out great that it was only 1 point. So I'm going to box this in just so we don't get this information mixed up with the rest of the problem because now we're going to talk about the boundary. And when we're talking about the boundary, we're talking about the Lagrange multiplier. And that's where that whole side comes in now. So this problem here is a mix of 4.8, is it 4.8? Hang on. Along with 4.7. So it's both of them that I'm dealing with for this problem. This problem I did on the interior here is from 4.7. Now we're going to do the part of 4.8. So now we need to find our g. Now we need to define our g. So our g of xy is going to equal x squared plus y squared minus 16 equals 0. So now we're not necessarily using this inequality anymore. And honestly, I forgot about that, to at least to talk about it in terms of the interior. Let me do that before I continue. Because this said less than or equal to 16, I know this is a circle here of radius 4. That's how far I'm going out. And if I look at my critical point, it was 1, 0. So it was within the radius 4 circle. So that's why it was okay. I'm sorry I didn't mention that earlier. That might be helpful here. Because not all critical points I end up with are critical points I have to check. Only the ones that are within the constraint that we see here. So be careful of that, because I could end up with 10 points, and honestly, I might only have to check 3 of them, as long as they're within the parameters. And this one wasn't, I knew it was, so I didn't really bat an eyelash on it, but those that are new to this might not realize that and say, oh, hang on, I don't have to care about that one, even though it's a minimum for the entire surface. So keep that in mind. All right, cool. So here's my g of xy, and now we're going to do the exterior, or the boundary, call it boundary. And that's what we deal with the Lagrange multiplier. So this is that 4.8, excuse me, 4.8. Okay, so now we need the gradient of g. And that's going to be 2x, 2y. There it is. And now I have to set those equal. So I have my gradient of f already. I'm just going to use the work I had from the previous, when I did the interior. Yep, so my fx is going to be 4x minus 4 comma 6y. And that's going to equal lambda 2x comma 2y. And again, now I'm going to set up all those equations. Here I get just 2. So now this is going to result in the equations 4x minus 4 equals 2x lambda. There's the first one. And the next one is going to be 6y equals 2y lambda. These equations look like they're going to be pretty nice, actually. I'm going to move everything over here, and this one here over. Same thing for the other one. Let's see. So I'll start with this one. 6y minus 2y lambda equals 0. Pull a 2y out, and I'm going to be left with 3, excuse me, minus lambda equals 0. That's a really nice start there. I started to think about the other one, but if I move that over, I still got this constant to worry about here. So I'm going to hang on to that for a minute and see what I can develop from this. All right, so again, like I'm saying too, just as I was moving back and forth in my mind that way, that's okay to do, so don't think you necessarily have to go one way or the other. If you go the other way, that's fine. If you can reason something out of that, that's helpful. Perfect. A lot of the answers we could get either way. Not always. Sometimes there's only one way to get them, but not always. Okay, so anyways, so this tells me y is going to equal 0, or lambda is going to equal 3. And when I looked at this other problem here, this is the reason why I was having an issue. I'll just kind of show it to you. So 4x, if I subtract the 2x lambda over, I still have this minus 4 equals 0. So now this doesn't give me anything I can factor out or anything like that. That's why I looked at it and said, oh, that's going to be kind of tough to see anything from. Like this one here, 2 terms I can factor. And that's what I've seen in this one. So that one might be a little more difficult to get something that's useful out of it. That will be helpful. Not saying I can't. It might just take a while to get there. And I might have to go through it anyways. I'll venture that in a minute as I see what I end up with. Okay, so anyways, so my y equals 0 or lambda equals 3. So now if y equals 0, now I'm just going to go right to the constraint here. The equation, the original. So the original equation says x squared plus y squared equals 16. Because remember, it's equals now because I'm only talking about the boundary here. So this is okay to just have the equal sign. I should have the equal sign. Okay, so anyways, now I'm plugging in the 0 for the y, so I get x squared equals 16. So x equals plus or minus 4. So for this first one, I get the ordered pairs negative 4, 0, 4, 0. And that's what I get for that one. So I'm going to get rid of that information. Need the space. And then now I'm going to look at where my lambda is 3. And that's going to be 4x. Now I'm doing it this way because I don't have an x or a y to plug in my constraint here. So I have to plug it in the other equation to get something I can use for that boundary. And that's going to equal 6x. So I can move the 4 over, so negative 4 equals 2x. So then x equals negative 2. So I get the other point here. Well, I don't get another point, I get the x, but I will get the other point when I plug it in, the constraint. And then this is going to be 4. And then when I move the 4 over, I get y squared equals 12. So y equals plus or minus 2 square root of 3. And that's going to be the ordered pairs. Negative 2 square root of 3, or positive 2. Oh no, sorry about that. That's also going to be a negative 2. That's my x right here. Okay. Positive 2 square root of 3. All right, so those are my 4 answers right now. So I went the other way, just in case you were curious over here. And I just wanted to show you, if I went the other way with it, this is what I could derive from it for x. And then I would get this equation and I would have to solve it for y, which I would still have 2 variables for lambda. I would have 2 variables, for this equation for y and the lambda. And if I wanted to go that route, I would actually have to solve this one for lambda, y equaling some function of lambda, and go through the same process with that. And honestly, I think that would just take a lot longer and be unnecessary for this problem. And if you're curious about that, you can pause it and work that out. Just so you know, I would have to find this equation, y equals some function of lambda, and plug it in for this, so I got lambda all by itself. So that's how that would have to be done. So now back to our problem. These are the 4 points that we have to consider that are all on the boundary. Now again, once I have my boundary points, I just have to plug them in my function to figure out if they're going to be maximums or minimums. And then I just go from there. And I'm just going to write them out, and I'm not going to show the math for these. But again, remember, I'll do it for the first one, just so you see how it works. And right, I picked the easy one, right? That's what teachers do sometimes. And the 4th one is down here. That's going to be negative 2, comma, 2 square root of 3. All right, so there's the 4 points. And honestly, we're just looking for maxes and mins here. So the biggest and the smallest. So then for the first one, I get 2, negative 4 is my x, squared, plus 3, 0 squared for my y, minus 4 times negative 4, minus 5. And that's going to give me So there's negative times negative is positive 16. So I can add that with this one because I'm squaring the negative on that one. So that's going to be 1632 there. So that's going to be 48 minus 5 is, 43. So it's going to be 43 for that one. Now I'm just going to do the rest of them and show you the answers. So now remember, everything we did was for the boundary so far. So what that means here is the largest values I see for the boundaries are going to be 47, and that's for the negative 2 square root of 3 numbers, or point, and then the negative 2 square root of 3 point as well. Those are the largest, and the smallest appears to be 40, and that would be a minimum on the boundary. But now we also had a minimum in here, in the interior, so we have to compare it with that one. So now we're going to have to do one more point. That's f of 1, 0. And then when I plug that in, we get negative 7. So this is going to be the absolute minimum. And these are going to be the absolute maxes. So we still have this information that's required for this problem. We classified all the interior points. It was a minimum. Let's usually say local minimum for those. And then we have an absolute max and an absolute min. And now I'm going to write those out for you to see what that looks like as a completed answer. Now all this work is going to be necessary to show for this problem. So don't think because I take it away that it's not essential or necessary to show. Just trying to fit everything in so you can see everything together here. So I would say 1, 0 is a local min. And I would say an absolute, I would say negative 2 square root of 3, and negative 2 square root of 3 are absolute maxes. And then I would also say that 1, 0 is an absolute min. So all this information would be necessary, but this would be your conclusion when it's all said and done.